Hello everyone, I'm Nex and welcome to our 15th lesson, Complex Numbers. We are slowly finishing off with the functions chapter. We will still occasionally throw in some properties as they are handy both in functions and calculating. Some graphs as they are quite handy to get an idea of why something is the way it is and how the value changes. For instance, we remember the exponential functions or something like that, or logarithmic. We see how the number increases as you increase the input. So today we go to the complex numbers. So there will be some graphs, but don't worry, we're not gonna be drawing much more. Well, except for this. So as we remember, there were those number groups. So natural numbers, whole numbers, integers, rational. Okay, here irrational ones are missing, and over the entire thing, real numbers. While this image from MathSpace is slightly poorly made for missing the irrational numbers, and the contrast is slightly, could be better because the white background and then the black writing and the green, that just doesn't fit too well. But yes, it does show how complex numbers are a superset of all other groups. We have learned so far at least, and in this lesson you will learn what exactly they are, why they exist, and pretty much all most important rules for calculating with these numbers. Plus some mentions of where they actually appear, just in case you'd like the, if you like them you can pursue the right course, or if you don't like them you can try to avoid them. So the first question is, why do they exist? And the answer is, as we remember, quadratic equations and zeros and the discriminant, etc. We had a situation where if the discriminant was less than 0, we had no real solutions. I think I mentioned these numbers back then and before and later, but today we finally learn what they actually are. So here is our example already written out for us. X squared plus 1, and we need to find its zeros. So we move 1 to the right, and we get x squared equals minus 1. But we know that it is impossible for real numbers. This is why mathematicians define a new unit. The unit is marked with a lowercase I, and is defined as the square root of minus 1, or that I squared is equal to minus 1. I is called the imaginary unit, but more on this a bit later. Why does that matter? Well, it allows us to define complex numbers. Most often we mark complex numbers with z, and each complex number is made from two parts. A is the real part, and bi is the imaginary part, which is sometimes also referred to as the imaginary number, but that doesn't matter for us right now. It is important to know that a and b are both real numbers. For now, this may be a bit weird and complex, but it really isn't. So all you have to remember is that complex numbers are built from two terms, or, well, 3 is a complex number technically, because b would be 0 for it. So a would be 3 and b is 0, so 3 is a complex number. So to make sense of this, we draw a coordinate system with all 4 quadrants. The main difference is in the labels. The x-axis becomes the real numbers axis, often marked as either real, like in the image, or just RE, like here. And y-axis becomes imaginary, or im. Here, y-axis, or the imaginary one, has a unit, and that unit is I. So always, it's like, I always has to be there. You either have to write it next to the separate values, so here on the image it should be 10i, 20i, 30i, 40i as we go up, and minus 10i, minus 20i, minus 30i as we go down. Or we could write this in a square bracket next to the marking of the axis, which is something we will cover more in physics chapter, but it's a nice foreshadowing. But yeah, there's no unit for the real numbers, and the unit for imaginary ones is I, but we usually write it here so it's more clear. Back to the number, like a random complex number, it is made from a, b, and I. And I assume some of you have figured out how this will work, and if you didn't, that's okay, that's why I'm here. The a, or the real part, is the number, is marked on the x-axis, or the real one. Hopefully my mouse-drawn sketch isn't too bad, so you can understand what I'm writing, meaning that a represents the x-coordinate of our complex number. Then we check the imaginary part, so bi. In this graph where I isn't written, we will just find b. Otherwise, we find bi. And I mark a random value here. Now that we have marked both the x and the y coordinates, or the real and the imaginary ones, we draw a horizontal line through the imaginary axis and a vertical line through the real one at the points marked, of course. And just like with normal coordinate system, we get our complex number as a point z with our coordinates like so. Just like real numbers are represented as a point on a line of real numbers, like remember the first video we made in the math chapter, complex numbers are points on a coordinate system where one axis is that real line from before, and the other one is the imaginary units, sort of like going from 1D, a thin line, into a 2D, a flat plane. In our example here, our z would be equal roughly 25 plus 20i. And yes, as I said, I did mention that in my first video, where I showed this hand-drawn on my iPad. So if this was unclear, you should go check my first lesson in math playlist, where I just explained the basic. I didn't really go that deep into it, but I think I explained it quite well. Unfortunately, there's a lot more of what we can do with them now that we know what they are. So next up is properties. We know by now that I squared equals -1. But what happens at higher exponents? So let's write a few out. My power of 9, we can already see a sort of pattern, so let me color it and give you a sketch. So they repeat in the powers of 4. So I to the power of 1 is I. When we times that by I, we get -1. Then multiply that with I, we get -I. And when we multiply with I again, we get -1 times -1, which is 1. And then we multiply with I again, and we see this entire loop repeats. So we can do something like this. But we can generalize it. So this is the generalization. So if you have some exponents over I, you can make a simple test to see the result. I'll also make the decision tree, as that may be easier to remember or find. But basically, whenever the exponent is the number after 1 that is divisible by 4, then you have just I, so I to the power of 1. When it's 2 more, it's -1. So when the exponent is a double of an odd number, when it's 3 more or 1 less, it's -I, and when it's divisible by 4, it's 1. Now I will order these around to give us a decision tree to solve any example in a matter of seconds. So let's say we have I raised to the power of x. First, we check the exponent if it's odd or even. Let's say it's odd first. When you have an odd number, so if it ends in 1, 3, 5, 7, etc., we check the last 2 digits. So, I don't know, a number 2025. We will only look at 25. Then we take one number less, so 24, and check if it is divisible by 4. This is a test for I to the power of 1, since it's 1 power higher than the multiple of 4. If the value that is 1 less, so 24, is divisible by 4, then we know that this is the type 1. So the result is I to the power of 1 is I. Meaning that this example, I to the power of 2025 would be I. The writing here for vertical line and x -1, hopefully you still remember that this means divides with no remainder, or that the right part is divisible by the left one. So I can put 12 here and that is correct, but if I put 13 or 7 or 6, it is not correct. So if 4 does not divide x -1 without a remainder, then it technically should divide x plus 1. If x was odd, of course, but we still try to make sure that it actually does. When it does, so when it doesn't divide x -1 perfectly, we know that it takes the value of x to the power of 3. So x is some random exponent. For instance, let's say x is 1. If we take 1 away, 0 is technically divisible by 4, but let's say x is 5. So 5 minus 1 is 4, so yes, it's divisible by 4. But if we take, for instance, 7, 7 minus 1 is 6. 6 is not divisible by 4, but 7 plus 1 is 8, which is divisible by 4. I hope you kind of see this relation. So the difference between the x plus 1 and x minus 1 is 2. So the jump between 1 and 3. Kind of like this. But yes, you can just do the yes test, and if it's not a yes, then it must be a no, unless you really did the yes test wrong. But let's go to the easier part. Next is even. Since we know all even numbers are divisible by 2, we do that first. But our next step is to see if we can divide that half value with 2 again. As we all know, 4 is 2 times 2. And if a number is divisible by 2 and then again by 2, that means it's divisible by 4. Therefore, takes the value of x to the power of 4. So, take x halves and see if that is an even number. So, another dividing by 2. If it's possible, then yes, it is. If it's not, so if you divide by 2 and you get an odd number, then it's I to the power of 2. But you remember, when dividing by 4, you always check the last 2 digits. So technically, you could just look at the last 2 digits of the exponent and analyze them. Is it divisible by 4? Yes, then we have I to the power of 4. If it's only divisible by 2, we have I to the power of 2. If it's odd, take 1 away. And if it's divisible by 4, it's I to the power of 1. And if it's not divisible by 4, then it must be divisible by 3. So it's like this decision tree. This is the tree. You can memorize this one, or you can make one yourself if you have any other conditions that make more sense to you. At the end of the day, it's what is the easiest way for you to remember it. This is for me probably because, well, 4 is 2 times 2, and the odd ones are just trial and error. You can also just... Actually, no, that's a method I mentioned later, so I'm not gonna get ahead of myself and double everything. So yes, let's try to solve a few examples. You can take a pause and try to solve it for yourself. But if you still need time to see how this is used and solving practical examples, that's completely okay. So let's get started. So we see 1110 is an even number. So I'll immediately divide by 2. And we get an odd number, meaning that this one is very easy. It is the same as I to the power of 2, since you can only divide by 2 and not by 4. So I to the power of 2 is minus 1. Next we have x being 12,345, which is an odd number. So we will look at the last 2 digits, so 45. Take the number that is 1 less than that, we get 44, which is divisible by 4, and this means that this is I to the power of 1. No remainder. This is our solution. You're free to fact check this, or you can take the slow route and take out multiples of 4 from the exponent until you get down to like x that is less than or equal to 4. For instance, in the second example, we can take away 4,000 about 3 times, so altogether 12,000, which leaves us with 345. Then we take away 200 because it's 4 times 50, and we have 145. Then we take away 120, and we're left with 25. Then we take away 20 to have 5, and then we take away 4 to have 1. This is slightly slower unless you're very versed with multiples of... But yes, either take the long way or the short way, whichever one you feel most confident in. And just like all other numbers, complex numbers can be calculated with, but since they're made of 2 terms, their behavior is something more similar to behavior of binomials, so the expressions with 2 terms. Let's get to it and see how exactly they work. Just like with binomials, we add or subtract the terms separately. It helps if we treat I as a variable, especially in these 2 operations. So I add 3 and 1 together, and then 2i and minus 4i. So the result would be 4 minus 2i as our answer. For our next example, we have 5 minus I minus 2 plus 3i. We take 2 from 5 and 3i from minus I, which gives us 3 minus 4i. This is basic addition, basic subtraction. There's nothing more complicated, just treat I as a variable in these examples, and that's it. Multiplication. Here we need to remember back to the distributive property. Basically, we will multiply each term or part of a complex number with each part of the second one. So we want to multiply 2 plus 3i with 1 plus 4i. So we use what we know and multiply each term from one number with each term from the other. So we have 2 times 1, we get 2, 2 times 4i is 8i, 3i times 1 is 3i, 3i times 4i is 12i squared. But if we can do some more with this, we can combine the imaginary units with each other. So we get 2 plus 11i plus 12i squared. And now you may be thinking, we are done, right? Well, not really, thanks to the property of I. Despite it being easy to work with as if it were a variable, it still has a defined value that is -1 when squared. So we can keep solving. And we get -1 times 12, which is -12. We can add these two now together and we're left with -10 plus 11i. Meaning that multiplication is just multiplication with extra steps. Next operation is division. Here we will learn something I think I have mentioned before. Some of you may have been wondering if there exists an elegant formula for this, and it does. It is a sum of the squares. But let's not get ahead of ourselves and let's see it on an example. We want to divide 3 plus 2i with 1 minus I. Now, since I is basically a square root of -1, important part here being a root, we want to do what we learned in radical functions, that is, rationalizing, not our purchases and bad decisions, but the fraction. We did that by multiplying the radical or binomial, which helped us get rid of any roots in the denominators. But how can we get rid of an I here? We can't just multiply with I, because then we have I plus 1. And if we remember multiplication, we multiply each term with each term from the other number. So we need something that will make the real from the first and the imaginary from the second be the opposite sign. And then the imaginary from the first multiplied with the real from the second. Basically just overcomplicating. The closest thing we have to this is the difference of squares, where a squared minus b squared is a plus b times a minus b. This formula gets rid of any cross products, so there is no mixed terms. So let's apply this rule here and multiply with 1 plus I on both sides. So on top we get 3 plus 3i plus 2i plus 2i squared, which when simplified gives us 1 plus 5i. And this is on top. As for the bottom, we get 1 minus I squared, so by this formula. Now we can simplify the bottom. Minus I squared changes into minus 1, which is a plus 1, leaving us with 1 plus 1. Do remember this. And then the result is 1/2, so the first term with the entire bottom part, plus 5/2, so the entire second part divided by the bottom of I. But let's look at the denominator here, and the last white fraction. Our A was 1, and our B was 1. And after we solved and simplified it using the difference of squares formula, we suddenly had the sum of the numbers. So we used the right part of the formula, but the result was different than this one, sort of. This means that incorporating complex numbers into the formula for the difference of squares gives us a formula for a sum of squares, which kind of makes sense as adding I to B doesn't change the fact that the cross products AB get cancelled, but its present in B squared changes it from a minus into a minus minus, which is a plus. So like this. And this is our new formula, the sum of squares, obtained by simply using the difference of squares on a complex number, or complex numbers, and realizing that I can help us change the sign that simply. Now that we know this, let's see what the significance of this is in complex numbers. Because obviously it's not just a formula, it must have a use. Conjugate and absolute values. Yet another few magic words and nightmares, right? Conjugate and absolute values. I can assure you that while they may cause nightmares, they aren't magical. But yes, hopefully you still remember when a few lessons ago, a bit more, I threw in the word conjugate randomly, and well, here it's where it's used. If z is a complex number written as a plus bi, its conjugate would be marked as z with a straight line over it, and its value would be mirrored over the real axis, meaning the sign in front of the imaginary term changes from plus to minus, or vice versa. A quick note on the marking for conjugate is a straight line over the letter, or even a bracket if you have a task in which you have to solve a problem and there's a conjugate over the entire thing, so you need to change the sign of imaginary unit at the very end. And the line is usually a bit longer, something like this. So the right one is more often used than the left one, but the left one is one symbol, while the right one is two, so my laptop can handle it and it will crash if I draw too many, so I'll just be using the left one, which is copy-pastable. But yes, usually you draw the line above it just straight, either the same length as the letter or slightly longer, but as long as you mark it correctly, it's all fine. Now, why would this be important? I hope that you know by now that I don't say things that aren't important unless I remember a fun fact that isn't important, but just fun to know. Now we can remember the formula for sum of squares and the conjugates, and we see that you can get a sum of squares, so a and b, from a complex number. But then again, why would this be important? So we remember the formula was a plus b times a minus b, so a number times its conjugate. Again, why this is important? Look at the third and the fourth word on the slide. Absolute value, which is the distance between two values, or between a point and the origin of the coordinate system or the line. So how do we know I'm speaking truth and not just random BS? Well, we'll have to check with the triangle and the Pythagorean theorem, which I hope we all know. So we have this, which is a basic part of the theorem, and are all familiar screenshot from the beginning, but with one more line, the diagonal, which is marking the distance between z and the origin. The distance is calculated with the absolute value, so let's replace c with it, like this. And now, to just get the distance, we take the square root of both sides. And this is another formula to know, which helps us calculate the distance from origin to the point. It's not really hard. If you do also forget it, it's very intuitive to get it from the scratch too, because it's just x squared plus y squared all together rooted. So kinda, yeah. Not really that complicated. When we get to vectors, these formulas are gonna be even more handy, absolute values all over, but that's actually like half a year or more away because I'm gonna have to take a break after I'm done with the math chapter, and vectors are kinda the introduction into physics, but still under maths. But yeah, let's not get distracted too much. Basically, we use the sum of the squares to get this formula from the conjugate property, and then we realize that the left part looks familiar to Pythagorean theorem. I can't speak today, sorry for this. And we replace the product of these two with c squared, and we saw that this is visible in the position of the point in the graph, so in the coordinate system. And then we decided that if a squared plus b squared equals c squared, so the distance between this and this, then c squared is basically the square of the distance between the origin and the point. Hopefully this makes sense before we move on to real-world applications. Despite the words imaginary and complex in the name, there is still some real-world applications to these numbers and various fields. The first one are engineering and physics, where complex numbers appear in different concepts, some that we will learn in physics, I think quite early on as well, and some in maths, such as oscillation, trigonometric functions. That's where I mentioned something with complex numbers, so next time almost. I think, no, within the next few months. Then in alternating circuit currents, so this is also something we'll do in physics. Not that much, but just enough. And I know this because I had to know this like a month ago for my exam in the current systems, so yeah. It's not that hard once you get the basic equations down, so don't worry. Then there's computer graphics, more commonly in 2D rotations and scalings. Of course, there's quantum mechanics and Schrödinger equation, as you see I here. Some weird symbols that we'll get to once we get to physics, quantum mechanics part of it. Don't worry, this is complex, but it gets easier, hopefully. Then in control systems, as the stability of the feedback system. And we see that all, or at least vast majority of these examples had something to do with waves, magnitude, direction, which when we get to trigonometry, we will see that I can appear in quite a few formulas. I guess it would be smart to cover vectors earlier, but I'll have that when we start physics chapter by adding it as a new math lesson, so the transition into actual practical stuff is easier because, well, physics is a lot easier to understand with vectors, because there's a lot of equations that make no sense unless you actually know the basics of vectors. And we see the, oh yeah, vector. But yeah, in trigonometry, complex numbers reappear through this equation. We didn't cover enough for you to be able to understand this just yet, but we do see some things that we already know. We see E, I, a weird circle letter, which is called theta, and is a Greek letter that most often appears in context of angles, especially in terms of waves. This isn't really important to know just yet, but I guarantee one day you'll understand this equation with all the knowledge I plan on sharing with you all. And yeah, I think when we start physics, or early into physics, you're gonna be able to understand this. I think that's like probably within the first 5 lessons, which is a few months, but who cares? But yeah, since we haven't done much math today, let's solve some examples here before the mini test, so hopefully you'll do well there. We have a product of 2 complex numbers, so we just multiply each term with each term. I will write I squared as II for now because it's just easier and to see and simplify, so I don't have to mess with the superscript and everything. But yes, multiply these together, we get +2, so the result is 8 + 1. Here is what I was talking about. The example wants us to find the conjugate of the solution to this fraction. Maybe this was poorly written, maybe I should have written like the line higher and bigger. But the next slide makes this a bit easier to see, because technically this could be understood as the conjugate of this value, but that's why we like brackets, because they specify what is done on what. First, we need to get rid of I in the denominator and separate the real and imaginary parts, and then change the sign of the imaginary part. I could complicate this further with absolute value, but then the absolute value of a conjugate is the same as the original, so it wouldn't really be making this too much harder. So let's just multiply, or use the law that we learned today, so the sum of the squares. We simplify the denominator. What is left in the top? We simplify that as well. And we get 10 plus 10i divided by 10, which is 1 plus I, and conjugate of this is 1 minus I. This is our elegant solution. The absolute value would be root of 1 plus 1, so a square root of 2, which one day hopefully I have enough time to make a short on how to represent distance, like irrational numbers on a straight line. But yes, so basically we use the sum of the squares rule here to get rid of the I in the denominator. Then we simplify the top and the bottom. We canceled out the 10, and after the fraction was gone, we basically separated the real and imaginary parts and took a conjugate, so the different sign of the imaginary part. And this was our result. Thank you so much for tuning in to today's lesson. Here is the mini test. I hope everything went well. And yeah, best of luck solving it, and I'll see you all on our next quest. Bye!